We are now going to talk about chemical reactions and how we actually describe them on paper. To do that, we have to have a chemical equation. And here's an example of a chemical equation. Chemical equations have kind of three parts. The first part, the beginning part, is what we react together. And so we call these components reactants. And when these two things combine together, when the reactants combine together, they make some other things. Whenever we have a chemical equation or a chemical reaction, whatever is made is what we call the products. Now, to show that we are going from these substances to this substance, we usually designate that with an arrow. This arrow shows it goes from left to right, so that means that the reactants are making the products. Some reactions can have the arrow going from right to left, meaning it's a reversible reaction. That shows that the products, or in this case the substances on the right hand side, make the reactants. And then we can also have a double-headed arrow, meaning that the reaction is reversible. So that means that the reactants combine together to make the products, and the products are combining together to make the reactant. But for the most part, and for our purposes right now, we are going to have a forward reaction where the reactants are combining together to make the products. In this case, you will notice that we have the formula of the compounds, and so here we have pentane, C5H12, and oxygen, O2. Now we also have these numbers here that are in front. Now there's not a number in front of this. It's understood that there's a number 1. What these numbers are the chemistry coefficients, or the chemical coefficients, that tell us how many of each of the compounds they are that are reacting, or how many of each compound is forming. So in this case, we have 1 molecule of C5H12, 8 molecules of O2, combining together to make 5 molecules of CO2 and 6 molecules of water, or H2O. So we will have these coefficients that tell us how many of each of the compounds we are reacting together, or how much of the products that we are forming. Another characteristic of chemical equations are what we call the phases. The phases are written as abbreviations in parentheses. So here we have the liquid for the L. G stands for gas. Other examples would be a solid, which we represent with the symbol S. So we have solid, liquid, and gas. And then we also have the symbol AQ, which stands for aqueous. Aqueous simply means that it is dissolved in water. So this AQ stands for an aqueous solution. So you may come across any of those symbols in a chemical equation, and you should be familiar with that. Now, whenever we have a chemical equation that we are writing, we always want to balance the chemical equation. And whenever we're balancing, we're satisfying the law of conservation of mass. The law of conservation of mass says that nothing can be created or destroyed in the universe. Mass is constant. So in this case, what we're going to be looking at are the individual atoms. In this case, we're going to look at the individual atoms of carbon, hydrogen, and oxygen. So here, this compound right here has 5 carbon atoms. We have 5 carbon atoms that we're starting off with. And so when we end, we should also have 5 carbon atoms. And we do that by putting a 5 in front of the CO2. This tells us that we have 5 carbon dioxide molecules. So that says that we have 5 carbon atoms. Now what about hydrogen? Hydrogen, we have 12 atoms of hydrogen here. There's no hydrogen in this compound. So what we're starting off with is 12 atoms of hydrogen. So we should have 12 hydrogen atoms that we end with. And so there's no hydrogen in the CO2, but we do have hydrogen in the water. For every water molecule, we have 2 hydrogen atoms, and this 6 tells us that we have 6 water molecules. So 6 times 2 means that we have 12 hydrogen atoms, so which is what we started off with. So we've balanced out the hydrogen by putting that 6 there. What about oxygen? Well, we have 8 oxygen molecules, so that tells us that we have 16 oxygen atoms. 16 oxygen atoms in the reactants means we have to have 16 oxygen atoms in the products. Now we have 2 compounds that have oxygens in them, so we have to combine those two, the CO2 and the water. So every CO2 molecule, we have 2 oxygen atoms. We have 5 of those, so that means we have a total of 10 oxygen atoms, for 5 CO2 molecules. And then we have 6 oxygen atoms in the 6 water molecules. So 6 plus 10 gives us 16, which 8 times 2 gives us also 16. So that means we have the same number of oxygen atoms. That tells us that we have satisfied the law of conservation of mass, so this equation is balanced. The balanced chemical equation here means that we have 1 C5H12 reacting with 8 O2 molecules to make 5 CO2s and 6 water molecules. Whenever you're balancing chemical equations, you have to remember something that we talked about a while ago is diatomic molecules. If you remember diatomic molecules, there are 7 diatomic molecules. And the way we remember the 7 diatomic molecules is from the periodic table. So on the periodic table, it starts at molecule or element number 7, which is nitrogen, and it makes a 7. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Well, that's 6. Our 7th one is hydrogen. Remember, hydrogen is usually always an oddball, so that's the case in this instance. So those are our 7 diatomic atoms or elements. And what that means is whenever we use those terms like nitrogen and oxygen, we always mean that we have 2 of those atoms bonded together. So if you're asked to write the formula for oxygen, you don't write simply O, we write O2 because it's a diatomic molecule. The same thing for iodine. Iodine would be I2 because it is a diatomic molecule. So we can remember it by starting at number 7, going down, making the 7, and not forgetting the hydrogen. Another way of remembering it is a mnemonic device, which I learned a really long time ago, and that is the simple I bring clay for our new house. And then that way you can never forget what the diatomic molecules are. Now let's do an example of balancing a chemical equation. So the chemical equation that we're going to balance is CaOH2 with H3PO4, and so these are our reactants, and this is going to make Ca3PO4, and we will have 2 of those, and H2O. Now there are some ways of helping us balance chemical equations. For one, you always want to start with an element that is kind of by itself. In this case, we have calcium. So we're going to start with calcium. We don't want to start with oxygen or hydrogen because that's our oxygen and hydrogen is in lots of different compounds. We want to start on a compound or an element in a compound that's just listed one time. In that case, that would be calcium. So we're going to start with calcium, and that will make things easier. Also, if you ever come across a reaction that has an element all by itself, for example, this one up here where we have oxygen all by itself, you wait and do oxygen last. You let the element that's all by itself, you hold off to the very end to balance that. Another trick that you can have is whenever you see groups of elements in the form of polyatomic ions, a lot of times you can group those together to help balancing. And so that's what we're going to do here. Notice that we have the phosphate, PO4, and we have a PO4 here, the phosphate ion. And so we're kind of going to group those together. Rather than counting the individual oxygens and the phosphorus, we're just going to count phosphate as a group. And that kind of helps things move along with the balancing and helps you not keep track of all the different elements. Now, and whenever you do balance something, you always want to make sure that you have the same number on both sides. That's what we're ultimately trying to find. So in this case, we're going to start with the calcium. Calcium, we only have 1 calcium atom here. We have 3 on this side. So to get 3 on this side, we put a 3 in front. We change the coefficient. Never, and I will repeat, never change the subscripts on your compound. Changing the subscripts changes the identity of the compound, and we don't want to change the identity. All we want to do is show that we have more of those particular compounds. In this case, we have 3 calcium hydroxides. And so we have 3 calcium atoms and 3 calcium atoms. So our calciums are the same on both sides in the reactants and the products. Now let's look at the PO4s. So there we have a 1 PO4 here, and we have 2 PO4s. So to balance this out, we're going to put a 2 here. Do not put a 2 down here. because that will change the compound. We want to put a 2 as a coefficient. So we have a 2 here that says we have 2 PO4s. So we have 3 calciums, 2 PO4s, 2 PO4s. So this part here is balanced. Now what about the hydrogens and the oxygens? Well, if we look, we're not going to count these oxygens in this PO4 because we took account of that whenever we grouped the phosphate polyatomic ion together. But we want to look at the hydrogens here. We have 6 hydrogens in this compound. Yeah, we have 6 hydrogens over here too, so that gives us a total of 6 plus 6 is 12 hydrogens. And we also have 3 oxygens, or actually we have 2 times 3, so that would be 6 oxygens. So we have 12 hydrogens and 6 oxygens, and to get that, we simply need to put a 6 right here. By putting a 6 here, that gives us 6 hydrogens, which we get. We have 12 hydrogens over here, so we have 6 in this compound and 6 right here. 6 oxygens, and we have 6 oxygens right here. The oxygens for this was taken care of with the PO4, so we don't need to worry about that in this case. So this right here would be the balanced equation. We have 3 calcium hydroxides, 2 phosphoric acids, makes 1 calcium phosphate, and 6 water molecules. This is a balanced equation. So let's do one more example. Let's do an example of C4H10 plus oxygen goes to CO2 and water. So this is just like the problem we did at the very beginning of this video. So what we're going to do is when we look at this, notice we have oxygen all by itself, so we're going to leave that for last. It's almost always a good idea to leave oxygen last whenever you're balancing a chemical equation. We're going to start with carbon because we see we have carbon here and carbon here. We could start with hydrogen. It doesn't really matter because hydrogen is in 1 on both sides. So carbon or hydrogen doesn't really matter. Oxygen, again, we're going to leave last because it's by itself, and oxygen is in 2 things over here. So let's start with carbon since it's first. There's no reason other than that. So carbon, we have 4 carbon atoms, and so we need 4 carbon atoms over here. So we're going to do that by putting a 4 in front of the CO2. So now we have 4 carbon atoms. Now what about hydrogen? So hydrogen's next. We have 10 hydrogen atoms, and so over here we have 2 hydrogen atoms. So to get 10, we simply put a 5. So putting a 5 in front of the water, we have 10 hydrogen atoms and 10 hydrogen atoms. So that balanced out the carbons and the hydrogens. Now what about the oxygens? Here we have 4 CO2s, so that tells us we have a total of 8 oxygen atoms for that particular portion. And then for this one, we have 5 oxygen atoms. Now 8 plus 5 gives us 13. So to get 13 over here, we would have to write 13 over 2. Now, it's never a good idea to have a fraction as a coefficient. We do not want fractions for coefficients. So to get rid of this fraction, what we're going to do is we're going to multiply everything by 2. And that will always be the case whenever you have an even-odd scenario where we have an even number of oxygens. Here we had 2, and then on the right-hand side we had 13. To balance or to get an odd number even, we just double it. And so that's what we're going to end up doing here. We're going to double everything, and when we do that, remember there's a 1 here, so we're going to change that to a 2. 13 halves times 2 gives us 13, so we're going to rewrite that as 13. This 4 changes to an 8, and this 5 changes to a 10. Now let's just double check and make sure everything is still good. We have 8 carbons right here, and then we have 8 carbons here. We have a total of 20 hydrogens right here, and we have 20 hydrogens right here. And then what about oxygens? We have 26 oxygens, and then over here we have 8 times 2 gives us 16, and then 10 oxygens. 16 plus 10 gives us 26. So 26 oxygens in the products, 26 in the reactants. Everything is balanced. We have satisfied the law of conservation of mass. One other thing to note, whenever you're balancing chemical equations, the coefficients, remember there can't be any fractions. If there is not a coefficient there, then we understand there to be actually a 1. And then also, whenever you're balancing, you never want to have multiples. So you want the least common multiple of your reaction. So for example, let's just do one more real quick. Let's do a simple one. Let's do hydrogen plus oxygen goes to water. So H2 plus O2 goes to H2O. And so let's say, for example, we're like, okay, well, you know what? I want to go ahead and say we have, let's do a 2 there, and that gives us 4 oxygens, and that gives us, put a 4 there to give us 4 oxygens, and that says we have 8 hydrogens. So to get 8 hydrogens over here, we have to put a 4. Now that right there is balanced. We have 8 hydrogens, 4 oxygens, 4 oxygens. But notice we have 4, 2, 4. That's not the simplest ratio. We could reduce that down to 2, 1, 2, and that would be the simplest ratio. And so whenever you're balancing chemical equations, you always want to have the lowest possible numbers as your coefficient. So the proper balanced equation here would be 2, 1, 2 for the hydrogen, oxygen, and water. So remember, always have the simplest ratio of coefficients. Always remember, you cannot have a fraction as a coefficient. We want to get rid of all fractions and make them whole numbers. Remember that remember your diatomic elements. We always have 2 of those whenever we're writing the names. And to help ease and to make things easier when balancing, group your polyatomic ions together.